Hi. The question states that consider a gaseous cloud, a spherical gaseous cloud of mass density rho r in a free space where r is the radial distance from the center. The gaseous cloud is made of a particle of equal mass moving in a circular orbit about the common center with the same kinetic energy. The force acting on a particle is their mutual gravitational force. If rho r is the constant in time, the particle's number density in r is equal to rho r by m is, and the g is the universal gravitational constant. Okay, so here we have to find out what is the value of number density. Okay, so let us take a spherical volume of radius r having the inner mass as m, and let us consider a particle having a mass small m and speed v. Since it is moving in a circular path, so definitely the gravitational force would act as a centripetal force which will facilitate it for circular motion. Okay, now that gravitational force will be balanced by its centrifugal force when we are talking about the frame of the point itself. Then centripetal force will be mv square by r, and the gravitational force will be mg is the gravitational constant. Capital M is the mass of the sphere or gaseous cloud of radius r. Small m is the mass of that small particle which is revolving, which we have considered here. R square, r is the radius which is given here, and that is equal to mv square by r. Okay, so mv square can be written as 2 times kinetic energy, which is kinetic energy means mv square by 2. So 2 times kinetic energy will be mv square. Okay, so I'm just rewriting in the form of kinetic energy because which is given in the, which is constant in the question. Fine. So we will calculate, we'll rearrange it, and we'll get the value of m. Now differentiate it with respect to r, then we'll have dm as 2k upon gm into dr. Fine. So this is the dm in the equation form. Now how do we calculate that dm? So suppose take a small take another layer of the cell having a thickness dr. So that this is the radius r, and go a small distance dr and consider a thin spherical cell. So the mass associated with this thin spherical cell will be the mass, that is small mass, which is dm. Okay, because the m is the mass of a spherical gaseous cloud having radius, this is a small r. So definitely dm will be just, it is the small extra additional amount which we are putting over it. Fine. So this dm can be written as the density at this particular r into the volume of this spherical cell. Fine. So this dm can be written as density at r, the volume can be written as 4 pi r square into dr. Okay, so this will be dm, and relate with this formula, the dr will get cancelled out. Then we'll get the value of density with respect to r. See, kinetic energy is known to us, g is the constant, small m is the constant. So we know that density is inversely proportional to r square. So if we just divide the density by mass of that small particle, then we'll get the number of particle in that spherical volume r. Okay, so if we just divide it, then we'll get nr as this value. So hence option B seems to be correct. So I hope it is clear to you. Thank you.